Welcome back to module 3. We are discussing how to create Wavepacket because Wavepacket is the actual representation of a particle in quantum mechanics. And to represent an Wavepacket, we need at least 2 plane waves. Here we have taken 2 plane waves with slightly different energies, and we will write down explicitly the linear combination of these two, e to the power I. Now k1 is given by this, so it's going to be k naught plus delta k x e to the power minus I e naught plus delta e t by h cut plus e to the power I k naught minus delta k x e to the power minus I e naught minus delta e t by h cut. So this is the expression we have for the Wavepacket, because we have to linearly combine them. And one can further simplify this as e to the power I k naught x e to the power I delta k x e to the power minus I e naught t by h cut e to the power minus I delta e t by h cut plus a e to the power I k naught x e to the power minus I delta k x e to the power minus I e naught t by h cut e to the power I delta e t by h cut. So now I can write down a e to the power I k naught x e to the power minus I e naught t by h cut, then e to the power I delta k x e to the power minus I delta e t by h cut plus e to the power. So this 2 has been taken out. So remaining part is going to be e to the power minus I delta k x into e to the power I delta e t by h cut, which is nothing but a e to the power I k naught x minus e naught t by h cut multiplied by e to the power I delta k x minus delta e t by h cut plus e to the power minus I delta k x minus delta e t by h cut. This is nothing but e to the power I theta plus e to the power minus I theta, which is given by 2 cos theta. So if I write it down like that way, then this Wavepacket, the final form of the Wavepacket, I get e to the power I k naught x minus e naught t by h cut, then 2 factor is coming here, and then cos delta k x minus delta e by h cut t. This is the final form of the Wavepacket. this form has two components. This is just a constant. It has this component, it has this component, and this both components, if we compare these two components with the plane wave, both components are representing a plane wave. But there is a difference. The difference is that here the variation depends on k naught, here the variation depends on the difference. So one is slowly varying, another one is fast varying components. So this is the final form of the wave packet, a simple form of the wave packet. And if we look at that, as I mentioned that two slightly different energies, which means slightly different k, and slightly different k means slightly different. So k is actually 2 pi by lambda. So their matter wavelength is different, which is shown here by this red and blue lines. So with two different energies, two matter waves are interfering with each other to manifest one particle in quantum dynamics, in quantum mechanics, and we see that k naught equals k1 plus k2 divided by 2. It is the average of these two, k naught, and delta k is k1 minus k2 divided by 2. It is the difference between these two. So this variation would be slow than this variation. So what does it mean? I have two different plane wave components presenting the wave packet. It means that here we have to see this figure. This slowly varying component is this one, which is giving me the envelope function, this envelope function, and fast varying component is there, which is giving me carrier wave. So in a wave packet there are two components I have. How do I draw the components? One component is very slowly varying. Another component, this is just to draw, this is still a slowly varying component. Okay. Another fast varying component I have, which is very quickly varying within this envelope, very quickly varying. Like this way. So this part is slowly varying and this part is fast varying component of the wave packet. And this is called envelope, slowly varying component, and fast varying component is the carrier wave. So these are the terms which we'll be using to represent the wave packet, the particle in quantum mechanics. Now the velocity of a wave packet will be defined based on these two components. First we will go for phase velocity. Phase velocity for a wave packet will be defined as the velocity of the constant phase front of the fast varying component. So this carrier wave, every particle, every quantum particle will be represented by wave packet, and in wave packet I have two different components. One component is very slowly varying, another component is very fast varying. This fast varying component is called the carrier wave. Question is, what is the velocity with which carrier wave is propagating? That is represented by the phase velocity of a wave packet, and that's how can I calculate that one? It is just the definition, coming from the definition, velocity of the constant phase front of the fast varying component, and fast varying component is here. So all we need to do is that this fast varying phase we have to write down and take the first derivative and make it 0. That's the way we have been doing always. So first derivative of this fast varying component is going to be 0, which is nothing but k naught dx dt minus E naught by h cut. I get phase velocity of the wave packet. This is the phase velocity dx dt. That is going to be E naught by h cut k naught. And we know that E naught, I can get an E naught expression. E naught is going to be h cut square k naught square divided by 2m. So I get phase velocity to be h cut k naught divided by 2m. This is the phase velocity of the wave packet. So what does it mean? I will show one more time. This is the particle which is having two components. One component is the envelope component, which is varying very slowly. Another one is fast varying component, which is varying very quickly. Now question is, what is the velocity with which this component is propagating, and what is the velocity with which this component is propagating? These two components are separately propagating, independently propagating, and we are trying to find out what is the velocity of individual component in the wave packet. Velocity, this phase velocity of the wave packet is represented and is given by this value. We will go for the group velocity. As usual, the definition of group velocity comes from the velocity of the envelope function, that is called the group velocity. So velocity of the envelope function, and envelope function is coming from this. So total phase, it is a slow varying component. Total phase is going to be delta k x minus delta E t by h cut. So the first derivative is going to be delta k dx dt minus delta E by h cut, or Vg, group velocity is going to be, this part is group velocity, is going to be delta E by delta k h cut. So if I take the infinitesimal variation, then I can write down the same equation as in a derivative mode, dk 1 by h cut. This is the group velocity represented by this equation. So we know the equation E as h cut square k square by 2m. We can take the first derivative of E with respect to k, because here I have to plug that in. If I do that, then h cut square 2k by 2m, which is nothing but h cut square k by m. And if it is taken to be at E naught, then it is going to be k naught. So I will be able to write down h cut square k naught by m multiplied by 1 by h cut, which is nothing but h cut k naught by m. This is the group velocity of the particle. So I will remind phase velocity of the particle, phase velocity. So this is the particle in quantum mechanics, represented by the wave packet, and I have a phase velocity, which means that what is the velocity with which. So this is the way we represent the particle in quantum mechanics, which is nothing but the wave packet. It has two different components. Each component is propagating with the same with its own characteristic velocity, and this carrier wave, which is varying very fast, it is moving with the phase velocity, and envelope function, which is very slowly moving, it is moving with group velocity. And these are the two differences we have. So phase velocity expression which we have is h cut k naught divided by 2m. This is the phase velocity we have got. On the other hand, group velocity, we are getting the expression h cut k naught by m. If I compare now with the previous classical velocity, which was calculated to be h cut k naught by m, what we see is that now classical velocity is actually represented by the group velocity. So, when I say that a particle is moving in quantum mechanics, its envelope function is moving at the classical velocity, but its carrier wave is propagating with a different velocity. That is why these two are not locked anymore. They are not like this way, their velocities are different. This carrier wave is propagating much faster velocity, and that is why when it is propagating, it is changing this tip and the tip of the envelope function, they are actually changing with respect to each other. So, that is the manifestation, that is the meaning of two different velocities of a particle in quantum mechanics. One velocity is represented by group velocity, which is nothing but the classical velocity. Another velocity, phase velocity, is the velocity of the constant phase front of the fast varying component or carrier wave that is moving in a different velocity, which is with a phase velocity. So, with this understanding, we will move forward and we will ask the same question. Remember, we started this part representing the wave packet because the plane wave solution failed to represent the particle in quantum mechanics. Now, after getting this new solution, we can ask the same question: is there any strange consequence we get from this? So, first of all, we will check what is going on with the probability density. Probability density for this wave packet will be given by absolute square of the absolute value, and that is nothing but 2a cos delta k minus delta E t by h cut whole square. Now, rho is, it depends on x and t. That was the requirement we had always. The wave function cannot be observed experimentally. I can observe only density, and in quantum dynamics, density should change as a function of time. This form is allowing me to see the change in density as a function of time. So, this is acceptable, definitely acceptable form of the particle in quantum mechanics. Second part, we had a contradiction in plane wave solution. In plane wave solution, we couldn't understand why a particle should have two different velocities. We didn't understand that. Two different derivation, two different ways we can think of getting the solution, and we got two different solutions. So, same particle having two different velocities in the form of plane wave is meaningless. That is just a mathematical artifact, or we cannot accept as a physical solution. But here we have understood that Vp and Vg, I can have two different solutions. I can have two different velocities of the particle. These two velocities are representing two different components of the particle. One component, the phase velocity, is representing the fast component, which is the carrier wave, and Vg is representing the slowly varying component, which is the envelope function. Because every particle has two components in quantum mechanics. because it is represented by the wave packet, and wave packet has two different components. One component is fast varying and another one is slowly varying component. So this is now understandable. We have understood the meaning of it. Third one question is whether this is normalizable or not. Minus infinity to plus infinity, 4a square cos square. I will not show this derivation, but clearly cos square function can be integrated and I can get certain value of a. This is going to be a finite value, not going to be 0. So finite positive number, which means that this wave function is normalizable. And requirement fulfilled for the quantum dynamics. A form of the wave function should be normalizable for an acceptable solution to the TDSE. So based on this analysis, now I go back to the first slide. I started with this slide. Classical mechanics, when I in the classical mechanics or in our daily life, when I say a particle, I represent like a ball moving along the direction x. But in the quantum mechanics, I can have a particle, but the particle cannot be represented with the ball. I have to represent with a localized matter wave, and localized matter wave is a consequence of the interference of multiple matter waves, which will allow the localization of the matter wave in position space. And the correct terminology for particle in quantum mechanics is the wave packet. So this is the picture which is a valid picture for the let's say free particle in quantum mechanics. But it doesn't need to be always very nice looking Gaussian shape here. I can have a particle like this also. It's just for the representation we have made this to be like this. So I can have as long as it is a localized matter wave, it can represent the particle. And actual shape of the particle, what kind of particle I will have, actual shape of the particle or actual shape of the wave function of the particle I should say, or the wave function of the wave packet, it depends on the potential it will experience during the motion. So with this preliminary idea, we will move to more rigorous treatment of the free particle as wave packet. Previously what we did, we have prepared the wave packet with the help of adding two matter waves. But free particle can have any energy, and that's why one can propose that okay, more rigorous treatment, mathematical treatment for wave packet should be, a wave packet should be represented as summation of a, I am now making it k dependent, the amplitude may vary depending on thing here. When I presented two interference of two matter waves to represent the wave packet, there I have made a to be independent of k. I didn't select different k, different a for two different waves. But to make it a general, I can have a to be dependent on k, and then I have the same thing kx e to the power minus I et by h cut, and this summation can be over all k, all possible k. That can be the correct representation of the wave packet, more mathematically appropriate or correct representation of the wave packet. And because k may adapt any value from minus infinity to plus infinity, and it can be continuously varying, So k can be from minus infinity to plus infinity, any value it can take up, because free particle, it can have any kinetic energy, and those kinetic energies can be carried out by a particle in quantum mechanics can travel with any kinetic energy if it is a free particle. And if it is if k can have any value, then instead of summation I can represent it in terms of this integration. It is just the integral form of the same idea, superposition of many matter waves. As a result of interference among the component plane waves, at one instant the wave packet exhibits large amplitude at one region of space due to constructive interference, and the region of constructive interference changes with time because of presence of the time dependent phase factor. So question is, can I have one analytical solution for the free particle wave packet if I consider this rigorous expression for the wave packet? So what will happen, let us see, at t equals 0 initial time, when the evolution didn't start, I should have wave packet x0 is nothing but minus infinity to plus infinity a k e to the power I k x. T equals 0, that is why this term will be gone. So I have this equation, and then this is integration over k. If I multiply, so I am just moving forward with the to find out the analytical solution to this wave packet. So I will multiply both sides by e to the power minus I will multiply both sides with e to the power minus I k dash x here also I multiply a k e to the power minus I k dash x. This is the mathematical trick I am going to use to get the analytical solution, and then I will integrate the both side from minus infinity to plus infinity with respect to dx. So if I do that, what will happen? Minus infinity to plus infinity psi x0 e to the power minus I k dash x dx equals minus infinity to plus infinity a k e to the power I k x e to the power minus I k dash x dk then dx. I can rearrange this integrand in a following way: minus infinity to plus infinity a k then minus infinity to plus infinity e to the power I k x e to the power minus I k dash x dx to dk. I can do that because this integration is over x and this integration is over k. And if we do that, then we can use one property of Dirac delta function and the property is following: delta function of k minus k dash equals 1 by 2 pi minus infinity to plus infinity e to the power I kx e to the power minus I k dash x dx. So, this integration here is related to Dirac delta function, or so I can write down minus infinity to plus infinity so this part I'll be write down in following way. I'll write down this and this part to be here, minus infinity to plus infinity psi x 0 e to the power minus I k dash x dx equals, here I will insert this Dirac delta function which is going to be minus infinity to plus infinity a k then multiplied by 2 pi delta k minus k dash dk, or this is nothing but 2 pi minus infinity to plus infinity a k e to the power e to the power a k delta function of k minus k dash dk. So, when a delta function appears inside an integral as one component of the product with a smooth function, this one will consider a smooth function, the value of the integral becomes simply the value of the integrand at the position of the delta function. So, this is another property of the delta function. If I have minus infinity to plus infinity fx delta x minus x naught dx, this is nothing but f of x naught. This is another property of delta function, and if I use that delta function property, I can write down this one to be 2 pi a k dash. Just like here, if it is a product of delta function and a continuous function fx, then this integration will give me the value of the function at x naught. Similarly, this integration will give me the value of ak at k dash, and that's what you have written here. So, a k dash is represented by 1 by 2 pi minus infinity to plus infinity psi, this is actually Wavepacket x 0 e to the power minus I k dash x dx. So, if I and k dash was selected arbitrarily, it can be anything. So, I can rewrite this equation as a in terms of k also, make it a general. In that case, it will look like this psi Wavepacket x 0 e to the power minus I k x dx. That's exactly what we have written here. So, with the help of this analytical approach, with the help of this Dirac delta function, property of the Dirac delta function, what we have got is that this is the general form of the wave packet, but in the general form one thing was unknown. The unknown part was AK, and what we see here, AK can be calculated from the initial wave packet. So, if I know the initial wave packet, I will be able to get the AK. Once I know AK, I can plug that in here and I can get the final wave packet at different time. So, this is giving me an analytical approach of of describing the particle, describing the motion of an wave packet when it is freely moving, and that is why we can use that equation. We will use that equation, but before we do so, as I have shown here, I need to know the initial wave packet. So, I have to start with a particular kind of particle. It can be nice looking Gaussian, so if it is nice looking Gaussian, then I will be able to plug that in here, that is my initial packet. And how this initial packet is propagated, this is at t equals 0, and then at different time how the particle would be look like, that I can calculate with the help of this equation, with this analytical approach. So, first thing I have to start with, the starting point for this wave packet dynamics is going to be the assumption of the initial wave packet. How does it look like? This is the form of the train of wave packet we have shown previously. It comes directly from the simple interference of two different matter waves, and we have seen that it has two different components, fast varying components, slowly varying components. All we are trying to do here now, every wave packet will have these two components, slowly varying component and fast varying component. What we are doing here now, we are using a slowly varying envelope approximation. Under this approximation, we can say that this this slowly varying component can be used as an envelope function. It is actually an envelope function, but instead of considering a plane wave form, I can assume a certain shape of that envelope function. In this case, I have considered a Gaussian shape. Why I am interested in Gaussian shape? Because if I consider Gaussian, which is represented by e to the power a x square, a simple equation e to the power minus a x square, if I use that Gaussian, then I can do many analytical integration without any difficulties. Integration, that minus infinity to plus infinity, Gaussian integrals are very well known and standard integral. If I take different shape, some other shape, some ugly shape, let us say like this, so in that case the fast varying component like this, in that case I cannot get the analytical solution, I have to go for the numerical solution. So, in this module we are trying to present the analytical form of the how the wave packet should move, and I have to start with a gaze, an initial wave packet, and the initial wave packet I can make it as a Gaussian form, where I can have this initial wave packet like e to the power minus a x square. E to the power minus a x square is the Gaussian function, which is centered at x equals 0. So, this is the Gaussian function, but this will not move. This will move only when I include this plane wave part also, e to the power I k naught x. Combining these two, this part will move. So, basically if I have a moving Gaussian wave packet, a travelling Gaussian wave packet, this is travelling Gaussian wave packet, then I have to use this initial wave packet to be like this. where this is the Gaussian function and this is the plane wave part, and then it is actually moving. So how it's moving? It will show like this way. At a particular time it will be like this, after a particular time it will be like this, after a particular time it will be like this. So it's different moving. It's time equals t1, this is t2, this is t3, this is t4, like this way it's moving. So traveling Gaussian has to be represented by this way. And if I start with a stationary Gaussian, then I do not need this plane wave part. I can use only a e to the power minus a x square. So this functional realization is very important to begin with the analytical solution of the Gaussian wave packet dynamics. We will now move forward in the next session. We will continue this and we will try to find out if I start with an initial Gaussian and if it is freely propagating, freely moving, what will happen to the shape of that Gaussian, whether it is broadening or compressed, we will find out in the next session.